Okay, gang, welcome back. We're here for another dynamics video. Today we're talking about cylindrical coordinate systems, and we're going to be talking about the equations of motion using the cylindrical coordinate system. So if you remember in the last video, we talked about a cylindrical coordinate system, what it is, and what the coordinates were. The x, y, z is now r, theta, and z, okay? And if you just go back to the last video to review that, okay? Now, just like we did before when we were talking about tangential, remember we were talking about tangential and normal components, and we would take the force equation and we would break them down according to the direction of acceleration. We'd have a normal acceleration direction, we'd have a tangential acceleration direction, and we would write our force equations in accordance to those components, right? We're doing the exact same thing, except this time we're going to use r, theta, and z. So it's the exact same kind of concept as it was when we used normal and tangential. We're just using different coordinates, okay? So same technique we've been using, just different coordinates. That's the only difference, okay? Now, since we have cylindrical with an r, a theta, and a z with all three components, we can have three different force equations. So we can write them for three different force directions, okay? That's going to allow us to solve for more unknowns too, isn't it? Okay? So you remember in rectangular, you had acceleration in the normal direction, which we called v squared over rho. Review that if you don't remember that, right? And then the tangential direction, which was tangential to the path of the object where it's accelerating, was dv dt, right? And that was usually a given value in the problem, was that tangential acceleration. Now in cylindrical coordinate systems, we're going to have the same thing. We're going to have these acceleration components. But of course, we're going to have three acceleration components. We're going to have an acceleration in the theta direction, which is we'll talk about that here in a minute. And then we're going to have an acceleration in the r direction, right? Here's r, and of course theta here. And then we're going to have an acceleration possibly in the z direction. And so just like we had equations for those components in the normal and tangential directions, we're going to have special equations here for the theta, r, and z directions, okay? So you see some stuff on here that we haven't talked about before. You've got r, and you've got theta double dot. I don't know what that is. And then you've got r dot and theta dot, right? Same thing down here. I've got an r double dot, and an r, and a theta dot squared, right? So what is that? Well, that is this, okay? That is something called the time derivatives, okay? The time derivatives. And so all you have, where's my pen? My pen? Let's use blue, okay? The time derivatives, and a lot of this information will be given in the problem. But theta is the angle that this device is a bar. It's the angle at which it's located, okay? It's just going to be like 30 degrees or whatever it is, right? So this theta is an angle, and if you take the derivative of that angle, you get an angular velocity. You have to go all the way back to the first videos to talk about the derivatives and how you get the derivative of, position is velocity. The derivative of that is acceleration, right? So theta is the angle. It would just be like 30 degrees. Theta dot would be the angular velocity. And so that's going to be in something like radians per second, okay? And then theta double dot is angular acceleration. That's going to be in something like radians per second squared, okay? Now to go along with these three things, I've got these three guys over here, these r's, okay? So r is just this. It's just this distance across here. Now we talked about how to calculate r last time. It's like the magnitude of the vector. It's how far it is across here, okay? So what is r dot? Well, think about that. The position of this ball as the angular velocity changes, right? So this guy is going to be like d theta dt, right? As this changes over time, then r is going to change as well, right? So I'm going to have a different r for the angular velocity as it changes, and then I'm going to have an r double dot is the position according to how it changes according to angular acceleration. Okay, and again, this is the derivative of that. This is the derivative of that. Okay, So step one on problems, and we're going to work one right here, is to find these 6 things. Okay, so that's what we're going to do first. We're going to find those 6 things. Okay, so we want to know, what does R equal? What does R dot equal? What does R double dot equal? And also, what does theta equal? Theta dot and theta double dot. Okay, so this is kind of our first step to figure out on these problems. Now let's look at this problem. So we're given here that a half-pound ball is guided along a path, and the path is this radius here. Okay, and we're given an equation of 2RC. Now RC is the radius of the circle times the cosine of theta. All right, so we're given an equation for that. And theta double dot, or theta dot rather, is 0.4 radians per second. So we're just given that, right? So 0.4 radians per second, okay? Theta double dot is 0.8 radians per second squared. 0.8 radians per second squared. It's given to us. We don't have to do any math here. When theta equals 30. Okay, so we're given that as well. Okay? Find the force of the arm on the ball, neglect friction. And then they gave us R sub C is 0.4 feet. Okay? So let's put that in here. So we have what? 2 times 0.4 times the cosine of theta, right? Hey, that's just a number, isn't it? So we know that guy already, don't we? So that's 0.8 times the cosine of 30, which is 0.693. So R equals 0.693, okay? And that would be feet, right? Okay? So step 2, we got to figure out what is R dot. And we're going to do that by taking the derivative of this guy. So R dot is a little bit harder to calculate here. So R dot is equal to dr dt. I think just a second ago I said d theta dt, but it's dr dt. It's how the radius changes with respect to time, which is equal to, according to the chain rule, right, dr d theta times d theta dt. Okay? Now this is calculus stuff. And if you don't remember calculus stuff, in the back of your Hibbler Dynamics book, right, there's an appendix C, and it goes over the chain rule. This is the chain rule, and it gives you 3 or 4 examples back here about kind of reviewing calculus. So if you don't remember the chain rule, you need to go back over that, okay? So that's a review for the calculus class. So in this particular case, what is that going to give us? Dr d theta. Here we have an equation with r and theta in it, so we got to take the integral of that, which is, the equation originally was so r equaled 0.8 cos theta. So what is the derivative? What is the derivative of that? Well, the derivative of that is 0.8, that stays constant, right? And then cosine theta, what is the derivative of cosine theta? Do you remember? Negative sine theta. And then we've got this, d theta dt, which just gives us theta dot, okay? So there is R dot, okay? Now, we can also, just like up here, we got a number for R dot. We can get a number for, just for R. We can get a number for R dot right here because we know what theta is, and we know what theta dot is, right? Okay? So, let's see if we can get that. So, well, let's just get our calculator. Okay? On. So we have 0.8 times the sine of 30, which is a half, isn't it? Yes. So we have 0.4 times theta dot, which is 0.4. So R dot is equal to 0.16, okay? So 0.16 feet, okay? Now we have to do one more thing. We have to take this and take the derivative of that one more time. And I think we're going to have to use the product rule to do that. So here we go for the next one. R double dot is equal to, let's just do it right here, okay? How about this? R double dot is equal to, okay? You remember the product rule? The product rule says we have 2 things multiplied together. We have this thing multiplied times this thing, right? So we take the derivative of this times that plus the derivative of this times that, right? That's the product rule. So we have to do kind of two pieces here. So let's do the derivative of that first. And the derivative of sine theta is cosine theta, so that becomes -8 cosine of theta. And then if I take the derivative of that, I'll also get a theta dot. Okay? And then times theta dot. Well, if I times theta dot and I have a theta dot, that means that I have a theta dot squared. Okay? Put your dot right over your theta. There you go. Okay? And then what? Now we're going to take the next thing, and so I'm just going to take this by himself, so minus 0.8 sine of theta, right? And now I have to take the derivative of theta dot. Well, the derivative of theta dot is just theta double dot, okay? That's a theta. So there is my equation for r double dot, okay? And that's using the product rule from calculus, okay? So we know what theta is, right? That's 30. We know what theta dot is. That's 0.4. There's another theta, and there's a theta double dot of 0.8. So again, that's going to give us a number. So let's calculate a number there, right? Okay, so what do we get? We get on. Did I put a negative over here? Oh my goodness, there's a negative right there. That could have been serious. And this isn't feet. I'm sorry, this is feet per second. This one's going to be feet per second squared. Okay, get it right, Dr. Hanson. Man. Okay, clear. So 0.8 times the cosine of 30 equals times, what is theta dot? 0.4 squared equals. So that's negative 0.111. Okay, negative. Just this bit right here. And then this part over here is, let's see. Let's do this. 0.8 times the sine of 30. Oh, clear, clear, clear. 0.8 times the sine of 30 is 0.4 times theta double dot, which is 0.8. So just times 0.8 equals 0.32. So minus 0.32. So if I add those together, plus 0.111, I get negative 0.431. Okay, so that goes here. Negative 0.431 feet per second squared. Okay, so we've got our R dot, our R double dot, our theta dot, and our theta double dot. Right, so that allows us to do some things like we can now calculate what these accelerations over here are, right? So we could calculate, let's see, a theta is equal to what? R, which is, okay, let's see if we can do this. Clear. 0.693 times theta double dot, which is 0.8 times 0.8 equals 0.554 plus what? 2 times r dot, let's see, negative, how do you do a negative on here? Negative 0.16 times r theta dot, which is 0.4 times 0.4 equals. So our theta, our acceleration in the theta direction is 0.4264, okay? And that's going to be feet per second squared, okay? And then our AR right here is equal to, all clear, AR is going to be R double dot, which is negative 0.431. Let's see, minus R 0.693 times theta dot squared. So 0.16 equals. So our AR is equal to negative 0.542 feet per second squared. Okay, so now we've got our accelerations calculated. We used all these values to calculate that. Next thing we need to do is draw ourselves a free body diagram of this ball and what's going on in order to analyze what the forces in those different directions are. So let's erase all of this, okay? And then we'll draw us a free body diagram of that ball. Let's see what's going on. Here we go. All right, let's erase all of this. We have our values written down over here, right? 4, 3, 1, 6. Yeah, we got everything written down. Okay. So let's look at a free body diagram real fast. Okay, what's going on to the ball? What's happening to the ball? Here's the ball. Okay. Well, we have a couple things here. Okay, here's this R direction, okay? It's the direction of the rod. We're trying to find the force of the arm on the ball. The ball, how does the arm push on the ball? There's only one way the arm can push on the ball, and that is this way right here, right? Perpendicular to that arm. So there's F, let's call it OA, from the origin to point A, okay? How do you find that, okay? What else is acting on this? Well, the ball has a weight of half a pound. We'll put a 0.5 there, okay? It has an acceleration in this direction, an AR, and it also has an acceleration in this way we'll call A theta. So that A theta is normal to the bar, right? The bar is trying to accelerate it in a direction always perpendicular to the bar, okay? And then there's a normal force from the wheel thing here that's pushing on the ball. And normal forces on round surfaces always go where? They always go through the center of the circle. So that normal force is like this. We'll call him N for normal, okay? And we know that if this is 30 degrees, right? Well, this length here and this length here is the same. They're both radii, right? So it's an isosceles triangle. So if that's 30 degrees, guess what? So is that. So this is 30 degrees, okay? And using trigonometry, this is also 30 degrees up here, okay? So I think we're ready to go. We've got two forces that we don't know. We don't know N, we don't know FOA. And then we've got these two accelerations, which we do know, right? Okay? So let's see if we can solve this now. Okay, so let's start off with, we have two equations that we're going to use. We're not going to use this one. We're in a 2D plane here. So we're not going to use this 3D one. So this one we're not going to use, but we are going to use these two equations here. Let's get a different color pen. And let's see if we can do this, okay? There's purple. All right, so let's use the R direction. So in the R direction, what forces do we have in the R direction? Okay, now this is the R direction. This is the theta direction, okay? It's just like a tilted coordinate system, right? So in the R, this guy has a force component in the R direction. This one does not. He's completely in the theta direction, right? And then this guy is going to have a component because this guy has a component like there and there. And this guy has a component there and there. So in the R direction, what do we have? We have N cosine of theta, which is 30. Let's put a 30 there, okay? Let's just put a 30 there. Okay? Going in the positive direction and then minus 0.5 times what? This guy here is actually the sine of 30. Okay? And that's all the forces in it. So that's equal to, right? Equal to M times A. So M is 0.5. And that's a negative, well, 0.5 divided by what? What? That's pounds, right? We need that into slugs, right? So 32.2, right? Feet per second squared, okay? Which will get that into slugs, times the acceleration in the R direction, which is negative 0.542 feet per second squared, right? Okay? And guess what? The feet per second squared are going to cancel out, leaving pounds on this side. Guess what N's going to be in? In pounds force, right? So that equation right there will allow us to solve for N, okay? So N is equal to, if you do the math there, 0.279 pounds, okay? So there's N. And all of that is from this equation, right? The forces in the R direction is equal to MA sub R, okay? Now we're going to do, here we go, sum of the forces in the theta direction, okay, is equal to MA sub theta. Same thing, okay? So all we're doing is just changing our components here. And so in the theta direction, what do we have? Let's call this positive theta. This is positive, okay? So I've got FOA, FOA, that's what I'm looking for. And then I've got minus this little component right here, which is what? 0.5 cos 30 minus 0.5 cos 30, okay? And that's all the forces I have is equal to, right, M, again, same thing up here, 0.5 divided by 32.2 times A in the theta direction, which is 0.4264. Okay? And then solve for FOA. So F, the force on the ball due to the bar OA is equal to, and what do I get if we calculate that? 0.300. Okay, and so there is the force on the ball. This is not very easy, is it, gang? Okay? A lot of calculus involved here and a lot of thinking. Chain rule, product rule. Woo! Okay, but we whipped it, didn't we? All right, here we go for the next video.